Hello and welcome back to our online courses on statistics. And today we will start inferential statistics with this topic, hypothesis testing. We will have three different parts within this topic. First, we will talk about estimation in general. Then we will see what is hypothesis testing about. And then we will refer to the most frequent kind of statistical test, the one sample t-test, or basically one of the most frequent tests, the t-tests. So first, about estimation, we will deal with the concept of estimation. Then we will talk about its error, the standard error of the mean, point, and we will learn what is point and interval estimation. So, basic concept of estimation means that we will make statistical estimates of different statistical parameters. We call them, in a general term, this theta. Within, we can expect to estimate central tendencies, the mean, the population mean, as the most frequent target of estimation, but also variability and other characteristics of the distribution can be estimated. What we will do? We will base our assumptions on a sample, a random sample selected from the population, and we will apply statistical methods to do so. So we will deal today with point estimation, meaning that now we say that the population mean is about, but a single number, let's say 105. Of course, we know it's not 105 exactly in the population, but that's what it is in the sample, so it's a good estimation for the population. The interval estimation is a little bit different because here we don't say a single number, we say an interval. We say that it's somewhere between 100 and let's say 110. This interval can be wider or smaller depending on many things. We will get into the depth of this in a moment. But so far, let's stay with point estimation, and here we will also refer to the standard error of the mean. Why? Because we know that this point estimation is a good estimate, but it's never a correct one. It always has its flaws, so we cannot make an exact estimate. We can make a good estimate and calculate its error, the standard error. So just reminding you, here we say that that point is our exact number, the estimated mean, and then we assign an error value to it. It's not for sure, the error can be larger or smaller in that respect. So let's see an example. Probably that's the most easy way to grasp this statistical term. There was a bunch of teachers who thought that the students in their high school had an outstanding IQ. Longfellow students are just better in that way. So based on a sample of, let's say, 4, which is quite small, but it's easier to, look through the data this way for us now, we can estimate that the population mean in this high school is a certain number, okay? We will use point estimation. Taking these numbers, we did a simple sample mean calculation, arriving at 115 as the sample mean. So we use that mean value, typical of the sample, to estimate the population mean of this high school. So the estimated population mean is also 115 IQ score. Now the big question is, what will be the standard error of this estimate? How good is it? And what is your hint just by looking at the raw number? It's always a good idea to kind of, make some pre-assumptions. Well, they're quite variable. So it's not like everybody has a high IQ. There's a very low one, there's a very high one, and some around the normal 100, which is the standard population IQ mean. So standard deviation of the sample can be calculated. It's 22.02. 22 is fine if you're reporting this in a conclusion. And if you have some doubts how this number, comes out, of course, I didn't just, calculate it on top of my head. And I've created a little practice video. Please link under this video. There's a link to the practice video in which I explain how we can use what we've learned in the descriptive statistics lecture and calculate the standard deviation. Based on the standard deviation, just by using this formula, we can calculate the standard error of the sample, which is important because that will be our flaw, our diversion from the point estimation. So that's a simple calculation. So it's around 11 points. So 115 is the estimated mean, and we have this standard error around 11. So let's practice a little bit how to conclude our results so far. We do have results. We did a point estimation. If this were a practice task or an exam task, you could have said that, okay, I've calculated the mean. It is 115 points. Is this value outstanding, says the question. Yes, it is. I mean, no doubt. It's clearly above the general average, 100 as in IQ points. But how sure are you about this result? Are you sure that these students in the school not these students that we took a sample from, but students in this school are outstanding? Well, here you might say that the small data set is rather variable. The standard error of the sample mean is in fact 11 points, which is quite high. Okay, so we're up to this point. Let's continue with more, delicate statistical methods. But first, let's look at the other type of estimation, the interval estimation. Here, we will say that the population mean is somewhere between 2 points. Okay, and when we define these range of values, we set up this interval, what we call confidence interval. Then we can say that we can state with reasonable confidence that the actual parameter here, the population mean, lies within these 2 points. Now, what is this confidence and how do we define this? Well, we define it by this simple mathematical rule. We take the mean and we take 2 standard deviations around the mean. Up, this is the plus in this formula, and down, this is the minus. Why is that? If you think back to the normal distribution and what we've talked about it, we said that within 2 standard deviations, we can find 95% of the population. So that's why we're taking 2 standard errors of that population mean. You can recognize the formula here. Only we're talking about here about the population deviation. Now, what about the confidence? How confident are we? Well, the interesting part that you have to define this a priori. So the most common level of confidence is 95%, but it doesn't mean that you cannot decide on a lower confidence, let's say 90%, or a higher confidence, that's 99%, for example, or any confidence that you like. probably we're just lazy and we will stay with the 95% confidence and interval. The opposite of the confidence is the error. We will call this the alpha, okay, the type 1 error. We will get to back to this point when we're doing hypothesis testing. But it's obvious if you're 95% confidence, you have 5% for error. So let's do our practice task again using interval estimation. So here we also have to introduce that the sigma, the population deviation, is 15 IQ points. We know that because that comes from how the IQ is set up. It revolves around 100, the standardized mean, typical of the population, and the standard deviations are 15 IQ points. So using that information, we can set up this confidence interval for the Longfellow population. We say that the confidence interval for the estimated IQ population mean of this specific school is 115. That's our mean from the sample, plus minus 2 times 15 coming from the sigma, divided by 2 because we have 4 subjects in the sample. That's the square root of the n, which is 4. Thus, we can arrive at 100 and 130 as the two out points of this confidence. So, taking that, let's conclude again. Does the general IQ score, the 100 points, seem different from this interval? Well, it's on the lower end, but it's still within the interval, so that's a no. Okay? Based on the above, do you think that IQ of students in this school is outstanding? Well, it seems so, but not really, because it's not out of this interval. Okay? We made a specific estimation based on interval estimation, and it just, it's not the 100, it's not out of that interval, so you will get a no as an answer. Let's continue and let's practice how to conclude this. It's very important that in statistical language you have your numbers, and then you have to come up with a plausible story that you could, sell to a journalist. And this is really the essence of what we want to practice on this lecture. Students show a well above average, that's for certain, based on a sample of 4 students. Don't leave that out, it's very important. However, the standard error of the mean is quite large. Okay, 11 points is a lot as variation. And this is the most important point for us now. The general IQ average is within the 95% interval estimation of the Longfellow population mean. You can also graph your results. We learned this when we learned descriptive statistics. We have the mean on the chart and the standard error of the mean as epsilon error bars. So let's turn to our next chunk of information here. Now we want to do hypothesis testing. This is the basis of every single statistical test that we will learn about. Let's start with the easiest yet seldom used test, the one sample z-test. First, we have to set up a statistical hypothesis, the null hypothesis, which I will explain in a moment. We have to know that whenever we do this, there's plenty of room for errors. We call them the type 1 and the type 2 errors. It's a good idea if you learn them and if you can differentiate between them. And last but not least, the one sample z-test. So, whenever we set up a statistical hypothesis, we have a statement. Let's start with a very easy one, interesting one, and it's very general. This is what you will probably test when you're doing actual statistics in your university life. So a group, let's say children participating in skill training, spoke, that's the name of the training, start to speak earlier than the US average, which is, by the way, 17.5 month of age plus minus 2 month. What is this here? We've learned that this is always the standard deviation. Okay, so here it's sigma, standard deviation of the population. So we need an experimental design. We will select a relatively large random sample of children from the trainees, and we will test for their first age of first speech performance. Let's not go into the details of how we will test it, although it's a very important thing if you're really doing this study, relying on parental reports or actually coding them in the laboratory. So these are details, but not for now. Our research hypothesis will say that the estimated population mean of first speech age in those in the spoke training program will be significantly, and that's a word we will have to learn from now on, significantly lower, not just lower, significantly lower than the US average. Thus, our statistical hypothesis is the same with just, formulas. We call this an alternative hypothesis. I will explain in a moment why it's an alternative. It's an alternative to the H-null, the null hypothesis. And that's simply saying that the estimated population mean of spoke is lower. Oops, that's the wrong direction, but I will correct it in your lecture notes. Spoke is lower than the US average. So what is the null hypothesis? The null hypothesis is the essence of statistical hypothesis testing, and it goes similarly to lawyers' logic. So the statistical hypothesis testing is based on indirect proof, meaning that our null hypothesis stated here will be true unless we prove it wrong. Okay, so that's the main idea. What is the null hypothesis? It's simply an equation. The estimated population mean of spoke children is exactly the same as as the general mean for speech starting age in the US. So we have to collect proof. If we do collect enough proof, we can reject our null hypothesis. If we cannot do that, then we have to retain it or keep it. So what are our alternatives? Either the spoke children start to speak later than the US average. We don't want that. That's our no alternative hypothesis, though it might become true. We cannot rule out this fact. That's why we're always using two-tailed tests when we are using hypothesis testing distributions. I will get back to these distributions later. But we assume H0 to be true unless we collect enough evidence to prove that it's not true, and in proving it not true, we want to prove that the spoke children in fact start to speak earlier than the US average. That's our goal here. So let's see how hypothesis testing works in the whatever statistical program, or you could calculate it by hand as well. This is what I will show here, but of course you can rely on statistical programs to do this for you. In goes a sample. That's the first step, and it's a good, probably big enough random sample. Then we do a mathematical rule for decision, simply a calculation. We will always come up with a calculated statistical value. So bear in mind that you always have a test value that you've calculated or the program calculated it. And when you're doing conclusions, you have to report it because it's a very important proof on which we rely our decision on. So whatever statistical test we use, we will have a value. Then we determine the so-called critical values, and you can see it on the two far ends of this distribution. The basic idea is that based on this 95% confidence interval, if the actual calculated value is within these 2 points, tough luck, you have to retain your hypothesis. You cannot say anything definite. You just say that I didn't find any significant differences, let's say. Now, that's this stuff. If it's within this area, then you keep the null hypothesis. But if it falls out either on the minus side or the positive side, then you can actually reject the null hypothesis. For example, say that the spoke children actually start speaking earlier or not, okay, then it's a retaining and you cannot say anything certain. Or the bad news if you actually prove that they start to speak later, because then the program didn't do them any good. That's a very unlikely event, but you cannot rule it out. That's a very important basic idea in this kind of statistics. What is the level of significance and what are the probable possible errors of the decision? Let's see them one by one. First, remember when you were out on the red fields, you could reject your null hypothesis. You could actually say something. Good news, but bad news is that you have a possible error. You could have rejected here the null hypothesis when it was actually true. You have a certain liability for this. It's not likely that you're doing this, but there's always a percent error, usually 5%, that we call alpha. Remember I said this when we were doing estimation. And in this case, you get statistically significant results when in reality there isn't any. So you come up with an erroneous conclusion. But everybody knows that, so it's not a problem, okay? We just have to bear in mind that whenever we do statistical testing and we come up with this kind of conclusion, rejecting the null hypothesis, this type 1 error is a possibility with alpha level of significance. When we retain the null hypothesis, we still can make an error because it's there, the possibility is there that there is actually a significant difference, but we couldn't or didn't recognize it. The probability of this is usually unknown, but it has some relation to alpha, and we can a priori make some calculations called the power analysis, not a topic of the introductory class, but there is a way to come across this probability, to lower it to an extent that we can accept. It's important that by reducing the type 1 error, so when we say that, oh, but I want to be very, very sure, my alpha should be just 1%, it's not really a good idea, because by that you raise the probability of the type 2 error. So it's a good thing to know and remember. So just to see an example, if we didn't report significant differences between language proficiency as, let's say, class A and B, what do you think? What type of error we might have made? So we didn't report any significant differences here. It's of course type 2 error, and it should be yellow because we kept the null hypothesis and there's a probability that in fact class A and B is different, but we couldn't spot it. So let's turn now to the one sample z-test. This is the easiest, most straightforward test, and it's a good way to learn about the different kinds of statistical tests. So remember the null hypothesis, and we can stay with this example. The spoke trained children start to speak exactly at the same time as the US children. But of course, that's not our purpose. We want to prove that the estimated population mean of first speech age in those actually training in spoke is significantly lower than the US average. And we should not rule out that there's another possibility, an other alternative hypothesis. How we will do the test? Remember, I told you there's always a formula that should be included in the test. Let's speak a little bit about this. It has a mean, the sample mean. It has this mu null. What the hell is the mu null? Well, it's basically our assumption, our a priori sort of level, the US average here. We could also test with this same test, kind of test, if students sleep more than 8 hours before an exam. I bet not, but is it a significantly lower sleeping time than 8 hours? That could be tested the same way. Here, the 8 hours would be our mu null. Then we have, so here, we have the data from the large training sample, which gave us the result of 16 months on average. That goes here. We have the 17.5 month from the US sample, plus minus 2 months goes here, down here. Okay, this population deviation. And the 400 students that we children that we actually tested goes down here under the square root. So, taking all this, we can perform the one sample t-test, where we always have some criteria, and these criteria are very, very important, because just like with cooking, if you don't use the right ingredients and the right kind of, let's say, pot or heat, then the whole thing will be ruined. And statistical programs will perform your test. It's just won't be a good test. So here, the criteria is that we have to have quantitative variables, obvious, we're square rooting and dividing, etc., which are normally distributed. We know sigma, well, that's good, we know sigma. We have a hypothesized mu null, and this is important, the standard deviation of the sample is similar to that of the population where the mu null comes from. Let's roll back a bit. No problem, 2 months, 2 months. It doesn't need to be exactly the same, but it shouldn't, be very different. There is a certain test to test that. We're not going into the details of testing whether the standard deviations are significantly different or not, but we do have a test for that. So we put in our sample, we put in this formula, the mathematical rule, and then we simply compare this calculated value to this pre-given values of 0.96 minus and plus. Easy as that. Let me remind you, z-test is the easiest statistical test. Here you just have to compare your actual calculated number to two existing numbers. Now, why is it 1.96? Well, because that's almost 2, and it's 2 standard deviations up and down where the 94% of the population lies under this distribution. So if we get our number within these 2 points, then we call it the region of retention. We keep the null hypothesis and don't say anything. But if we can reject it either on the minus angle or the plus angle, then we have something to say. Either that the estimated population mean of this specific sample who did the training are significantly lower, this part, or significantly higher, the other part. Okay, so let's do this with real numbers that we have from the actual data. 16 was the month where these children started to speak. We had 17.5 in the US general sample population. Sigma was 2, and so was the standard deviation of the sample, and square root of the 400 subjects that were the data taken from is 20. So if you do this calculation, it's 1.5 divided by 0.1. It's going to become a really high number, 15. Okay, so the result here is 15. Let's see where it fits. Does it fit between 1.96 and minus and plus 1? No, it's way out on this end. So, bottom line, we have to reject the null hypothesis, and we're not keeping this end of the bargain, but the other one to the right. And we will conclude that the training actually worked. We can say that the spoke program is a good one because based on the one sample z-test, z value, p value, it's enough if we say p is smaller than our pre-chosen level of error. Okay, this is the alpha that we chose a priori. We can, of course, take the exact p-value from the statistical program. That's also fine. Just don't write p equals 0.00 because that's not true. Probably it's a value lower than 0.000001. Okay, make sure that it's not 0. So based on these test values and the one sample t-test, in a sample of 400 trainees, the first speech age was significantly lower. That's our good news. What is lower? That's also important to state in your conclusion. It was 16 months plus minus 2 months. If you're stating a mean, make sure you're attaching a standard deviation to it. This comes from the sample. And where was this? In those training with the spoke. That's our good idea as compared to the US average. You not necessarily have to state what that was, but I've put it here just to be complete. So that's a good conclusion, and we will practice concluding these results based on just given details or actual statistical outcomes. So we will practice this along the way. Let's turn now to our last topic, the one sample t-test. First point, how is that different from the z-test? Why isn't the z-test enough? Why we need this t-test? Well, most often we don't know sigma. So that's an obvious point to have a test ready when you don't have sigma at hand. We will touch upon the student's t-distribution on which this test is based on, then to talk about the test and the degrees of freedom, which is an important attachment to this kind of test. So what if we don't know sigma? What happens then? Then we can still test the statistical hypothesis about mu naught. And please notice that the t-test is an exact resemblance of the z-test. The only difference is here. We don't know sigma, so we use the standard deviation of the sample. But because we do that, we have a little difference in the test itself. So the test value will be a t value and not a z value. In both tests, we have a mu naught. So that's how you can differentiate it from later t-tests, the independent and dependent samples t-tests that we will learn next time. And we can determine whether an estimated population mean of a population from which we drew our samples from is significantly lower than higher than the mu naught, this test value that we're using. So let's take a little detour to William Seeley Gossett, who published under the pseudonym of Student, thus the student's T distribution. He simply realized that when we estimate a mean of a normal distributed population in situations when we don't have the exact same sample size, then these distributions can be very different. Obviously, if the sample size is lower, then the marginal error is higher, so we have to kind of correct our estimation to deal with this fact. Thus, the normal distribution describes the full population, but the unaccompanied T distribution describes samples drawn from a full population, the sample. So, let's see how the t-test goes. It's exactly the same formula. We put in our sample. We have a mathematical equation which differs only in this respect. The standard deviation of the sample goes here. But please notice an important difference. Now we don't have preset values on our statistical distribution. We don't have a minus 1.96 and a plus 1.96, although when the sample is really large, then these values resemble these original Z values. However, for this test, when we do it, we have to draw an important, so okay, first let's stay with the criteria. Again, quantitative, normally distributed variables, but we don't have to know the sigma, and the standard deviation of the sample doesn't have to resemble this sigma. Okay, take in that. Whenever we do the test, and that's what the blue circle is about, we have to predetermine these two points, which will mark the area of retention and rejections, and these we call the degrees of freedom. For each problem, based on the sample size, we determine a different critical value based on the n-1, simple as that. And we can look this up on this in the what we call the student's T distribution table. Now, good news, the statistical program does this for you. So all you have to do is provide it with the right kind of test to do. And practice task is that teachers think the same problem that we've dealt with before, but now we will use the student's t-test to answer this question. Is the average IQ significantly higher than 100, our predetermined value in this school? We put the sample into the analysis. We can determine these t-values using the data, and this is what we get as a result. But here, the t-distribution will tell us that for this specific 0.5% error with the two-tailed tests, I told you we always use a two-tailed test for the given reasons, with the degrees of freedom of 3. Why 3? Because there were 4 elements in our sample. These numbers that go here and here on the minus and the plus side are 3.182. So if we put this in and apply our pre-given 1.36 as a result of the equation, then we can see that the t-values do not border these pre-given values. They do have this calculated value within the region of retention. So 1.36 lies within minus 3.182 and plus 3.182. So it's within this area. If we used statistical programs, we get the same results, only it looks a little bit different. So let's go through this as well. The number of elements, the mean, the standard deviation, the level of significance, which here is the actual error. What is this value? It's 26.6%. Did we vote on 26% error? No. We want our error to be lower than 0.05, that is 5%. So with this t-value and degrees of freedom, we cannot say that we found a significant difference. Thus, we can conclude our statistical test. Again, the outstanding IQ question. Students seem well above the average, let's give them that, with an average of 115 points plus minus 22. It's a way big standard deviation. However, based on the one sample t-test, t in brackets goes the degrees of freedom, 1.365, which is the actual test value, and with this p-value, which states that it's not significant, the level of error is higher than 10%. Thus, they're not significantly different from IQ point average in the population, which is 100 points. So please learn to conclude these, and your take-home message is that always base your conclusions on relevant statistics and report. Don't forget, these are some points that you have to always report. Number and characteristics of your observational units. 1. The statistical test you've used and its most important parameters. We will always state which are these parameters for these tests, the test value, and the level of significance that you've found in your actual calculation. Also the degrees of freedom in this specific test. And 3, last but not least, please give a precise conclusion with descriptives. What did you find? What was significant? If it's different, is it lower or higher? Is it in the expected range or not? So homework, after you do the seminar where you can actually use JAS to calculate these very easy statistical programs, have some other variations of the problems that we've done, and maybe even come up with your own practice problems. Thank you very much.